Okay, today let's have a look at the fourth lesson of chapter 3, optimization problems, C3L4. First of all, let's have a look at today's learning goals. So this is the last lesson of this chapter. After this lesson, you are expected to recognize and model a optimization problems using mathematical languages and solve an optimization problem using differentiation. Okay, first of all, let's give it a quick recap of the techniques to find global extrema. Because in solving such problem, usually you'll need to use the techniques to find the local extrema on a closed interval. In a closed continuous interval, the global or absolute extrema can only be achieved at critical points or endpoints, right? To determine the global or absolute maximum and minimum values of a function in a closed continuous interval, we can apply the following procedures. First, we find all the critical numbers, if any. Then substitute the critical numbers into that function. Then substitute the x coordinates of the endpoints of the interval into the function. Then find the global extrema values of the function from the function values in step 2 and step 3. Remember that the global or absolute extrema can only be achieved at critical numbers of endpoints, right? Then find the coordinates of the global extrema. Also note that a critical number of a function is a value a in the domain of the function for which either the first derivative at a equals 0 or the first derivative at a does not exist. If a is a critical number, the point AFA is called a critical point. Of course, sometimes FA does not exist either, right? And if the interval of interest is not closed continuous, the method is still similar, but we might need to use other methods such as analyzing the signs of the derivative. Okay, so basically this is just the abstract illustration of the techniques to find the global extrema. In order to solve a real-world problem, there also involves the first steps, which is to model that problem into the mathematical language. So first of all, let's have a look at some examples to illustrate this concept, okay? Okay, let's see this example. A lifeguard has 200 meters of rope and some buoys with which she intends to enclose a rectangular area at a lake for swimming, as shown here on the right. The beach will form one side of the rectangle. That means here, the beach forms one side of the rectangle. You don't have to use any ropes there, right? With the rope forming the other three sides, that means you should use your ropes to enclose these three sides. Find the dimensions that will produce the maximum enclosed area. If A, there are no restrictions on the dimensions. B, due to the depth of the water, the area cannot extend more than 40 meters into the lake. Okay, first of all, I'll give you 10 minutes to think about this question by yourself. After that, we'll have a look at the solution together. Okay, have you finished? Any ideas? All right, let's have a look at question A. If there are no restrictions, how we can find the global maximum? We can use the first derivative test, right? So we can let A denote the area. Then A is LW, which means because W is total length of the rope, 200 minus 2L, right? So that is written as L times 200 minus 2L, which is 2L squared plus 200L, right? For L is between 0 and 100. Note that because the total length of the rope is just 200 meters, right? So that means 2L, we need to ensure 2L is less than 200 meters. And of course, L is greater than or equal to 0 as well. So L is between 0 and 100 in the closed interval. The function AL is continuous on this interval. Then we can find the critical points. dA by dL, which is negative 4L plus 200. We can let the first derivative be 0 and find the critical numbers, which is L equals 50. Then we calculate the function's value at L equals 50. That gives us 5,000. Then we can find endpoints. In this interval, there are two endpoints. Then we find the function's value at these two endpoints. F0 equals 0 and F100 is also 0. Therefore, we know the global maximum. If we compare these three values, 5,000 is the greatest, right? Therefore, we know the global maximum is 55,000, which means when L equals 50 meters and W equals 100 meters, the maximum area of this area is 5,000 meters, square meters. Any questions? Okay, so let's consider question B. So what's the difference between A and B? In question B, there is a limitation. That means your length of L here cannot exceed 40 meters, right? Because it states here the area cannot extend more than 40 meters into the lake. Therefore, you can use a similar method. First of all, A is still can be expressed by negative 2L plus 200L. But this time, the limitation for L is between 0 and 40 inclusive. Then this function is actually a polynomial function, well, actually specifically a quadratic function, which is continuous on this interval, right? Again, we find its critical points. And we have already know that the critical points is when L equals 50, right? Therefore, we can see that there is no critical points in this interval. Therefore, if there is no critical points in this interval, that means the global extrema can only be achieved at the endpoints, right? So we find endpoints. One of the endpoints is 0, the other one is 40. So first calculate F0. This gives us 0, and F40 equals 4,800. Therefore, we know the global maximum is 4,800. That is when L equals 40 meters and W equals 120 meters, the maximum area of this area is 4,000 square meters. You understand? Okay, so because this question is not very that complex, you can also find the global maximum by analyzing the function itself, because this function is just quadratic function, which is opening down, right? If you don't use a differentiation method, you can still find the local maximum and global maximum by only analyzing its graph, right? Okay, so let's see a more complex question. So this time we won't, how about if we don't have a quadratic function? We can still analyze its global extrema by analyzing its first derivative. Okay, next let's have a look at this example. Suppose we have a cardboard box with a square base is to have a volume of 8 liters. Question A, find the dimensions that will minimize the amount of cardboard to be used. Question B, the cardboard for the box costs 0.1 cents per square centimeters, but the cardboard for the bottom is thicker, so it will cost 3 times as much. Find dimensions that will minimize the cost of the cardboard. Okay, again, I'll give you 10 minutes to think about this question by yourself. So note here, minimize the amount of cardboard means the surface area should be minimized, right? Okay, so can you solve each of the questions here? Okay, have you finished? Any ideas? Okay, let's have a look at the first question together. We can let letter A denote the surface area. And note that the unit for volume is liters, right? So correspondingly, we should use the square dm, right? Okay, so suppose the surface area is A, unit is decimeters, square decimeters, then AX is actually 2x squared plus 4xh, right? Because we have a surface here at the top and another surface here in the bottom. Therefore, we have 2x squared, right? For the other four surfaces, that's actually h times x times 4, right? Because we know the volume of this box is 8 liters, therefore we know x squared times h equals 8, right? Therefore, we know h should equal 8 over x squared. And then substitute h using this expression here. Ax is actually a function of x, which is 2x squared plus 32 over x, where x must be greater than 0, right? So the task is to minimize ax with respect to x. So first of all, we find its first derivative, right? First derivative of ax with respect to x is dA by dx equals 4x minus 32 over x squared. We let the first derivative be 0 and then find x is actually 2. This is a critical number, right? Then we let the first derivative be greater than 0 and find the interval is x is greater than 2. Because the first derivative is greater than 0, then this interval is an increasing interval. Then we let the first derivative be less than 0, then find actually x is between 0 and 2. This is a decreasing interval. Therefore, as we can see here, at this critical number, before and after this critical number, the function becomes from increasing to decreasing. Therefore, x equals 2 should be a before and after x equals 2, the function becomes from decreasing to increasing. Therefore, x equals 2 is the local minimum, right? And is also a global minimum because before that point, the function keeps decreasing. And after that, the function keeps increasing. Therefore, you can imagine that point is not only a local minimum, but also a global minimum. Therefore, we find this global minimum by substitute x equals 2 to ax. Then a2 equals 24. Then we know 224 is actually a global minimum, right? So we can make the conclusion. When x equals 2 decimeters and h equals 2 decimeters, then the minimum surface area is 24 squared decimeters. So be careful with the unit here. If we have liters here, you should use a corresponding unit for length, which is decimeters, right? Okay, have a look at the solution here. Any questions? Okay, then let's have a look at question B. So what's the difference between A and B? In question A, we want to minimize the amount of cardboard used. Okay, that means to minimize the total surface area. In question B, actually, we want to minimize the total cost, right? So first of all, you need to represent the total cost with respect to either X or H, right? So let's have a look at how we can do this. So note that the cost is 0.1 cent per square centimeters, right? Remember, if the volume here is 8 liters, that means 8 cubic decimeters, right? So we need to use a corresponding unit, which is squared decimeters. So we convert this number from 0.1 cent per centimeters to 10 cents per decimeters, except for the bottom, which is 30 cents per square decimeters, because it says the bottom costs 3 times as much, right? Then the total cost, let's use letter CX to denote total cost. CX should equal 30 times the surface area of the bottom, which is X squared, plus 10 times the other 5 pieces of surfaces, right? Which is X squared, that's the top surface, plus 4 times HX, that's the other side surfaces. And then simplify this expression. This gives us 40x squared plus 320 over x, where x is greater than 0, right? So basically, we want to minimize the total cost, Cx. So we need to find the global minimum of Cx when x is greater than 0, right? Again, we can use the first derivative to help us to find the minimum of Cx. The first derivative of this function is 80x minus 320 over x squared. We let the first derivative be 0. We can find the solution. X is actually the cubic root of number 4. So this is our critical number. Then we check the left side and right side of this number to see if the first derivative is greater than 0 or less than 0. So let's solve the inequality. The first derivative is greater than 0, and this gives us x must be greater than cubic root of 4. On the other hand, when the first derivative is less than 0, the solution is x is greater than 0 and less than cubic root of 4, right? So that means at that point, when x equals cubic root of 4, the critical number, the instantaneous rate of change is 0. And before that, the first derivative is less than 0. That means this function looks like this for the critical point. Then after this point, the first derivative changes sign to positive. That means after this point, the function keeps increasing, right? Something like this. And this is x equals square root, cubic root of 4. So x equals cubic root of 4 is a local minimum and also a global minimum, because before that function keeps decreasing and after that the function keeps increasing. Therefore, this point is not only the local minimum, but also a global minimum. Then we can find its global minimum by inserting x equals the cubic root of 4 to the Cx. So C of cubic root of 4 equals 120 times 4 to the power of 2 over 3, which gives us 240 times cubic root of 2. Therefore, we know the cubic root 4, 240 times cubic root of 2 is a global minimum, right? We have found the global minimum for our Cx. Therefore, we can make the conclusion here. When x equals the cubic root of 4 decimeters and h correspondingly equals to 2 times cubic root of 4 decimeters, then the minimum cost is 240 cubic root of 2 cents per box. Okay, any questions? I'll give you 2 minutes to have a look at the solution here. Okay, if you have no questions, let's have a look at another example. Okay, this time we have a railroad between two cities which carries 10,000 passengers per year when the fare is $50. If the fare goes up, the number of passengers will decrease, since more people will drive. It is estimated that each $10 increase in fare will result in 1,000 fewer passengers per year. The train cannot carry more than 13,000 passengers per year. What fare will maximize the revenue? And what is a maximum revenue? Okay, again, this is a typical optimization problem, right? I'll give you 5 minutes to think about this question by yourself, and then let's have a look at the solution together. So remember that first of all, you need to find your optimization target. You need to express the function first, right? Okay, you can start now. Okay, have you finished? Any ideas here? So first of all, what is your target of optimization? Okay, let's consider the solution for this question. We can let X denote the number of $10 increase in the fare, right? Then the number of passengers will be accordingly changed to 10,000 minus 1,000x, right? And the scope of x, the limitation for x is -5 to 10 because you need to ensure the number of passengers, this number is greater than or equal to 0, right? And also the fare must also be greater than 0. Therefore, the lowest number is -5, where the fare is 0, right? Then we can let R denote the revenue, which R equals 50 plus 10x times 10,000 minus 1,000x. So in order to optimize this equation R, we need to find its first derivative, right? First derivative is -20,000x plus 50,000. Then we can let the first derivative be 0. Then we find the solution x equals 2.5. Then we calculate the r at x equals 2.5, which gives us 56,250 dollars. Then we need to check whether this number is local minimum or local maximum. So we can apply the second derivative test. First of all, find the second derivative, which is -2,000, which is less than 0. Therefore, at this point, 2.5, 562500, first derivative is 0, second derivative is less than 0, then this point is a local maximum, right? Also, because the global maximum or minimum can only be achieved at local maximum or local minimum or at the endpoints. So next, let's check the endpoints, which is -5 and 10. First of all, find R -5. This gives us 0, and R10 is also 0. Therefore, if we compare this value, and this value, then we know this value here is the global maximum value of this function. Therefore, we say 2.5 and 562500 is a global maximum. Therefore, the conclusion is when your x is 2.5, then we know that the fare has been increased to 50 plus 10 times 2.5, right? Remember, the meaning of the x is the number of $10 increase in fare. So originally the fare is $50, then it has been increased by 10 times 2.5. That means when the fare is $75, the revenue can be maximized to $562500. You understand? Okay, have a look at the solution here. Any questions, just let me know, okay? Okay, if you don't have any questions, let's make a summary of today's key concepts. First one, solving optimization problems. You can just follow these steps, right? First, identify what the question is asking. Then define the variables, draw a diagram if it helps. Then identify the quantity to be optimized and write a equation. Next, define the independent variable. Express all other variables in terms of the independent variable. Then define a function in terms of the independent variable. Identify and state any restrictions on the independent variable. Then find the global extrema in the corresponding interval. And last, answer the question posed in the problem. Also note that the context of a problem often dictates the interval or domain to be considered. Last, answers should be verified to ensure they make sense, given the context of this question. Okay, so this is today's class. Do you have any questions? If not, please remember to complete and submit today's homework onto Google Classroom. Okay, so class dismissed for today.